Hello, everyone.
Hello.
How are you doing, Ashley?
Doing all right. How are you?
I'm good. We'll give a few more minutes for everyone to join.
Sure.
We did send out the announcement of this talk also to the CFA exoplanet list. So there are already a few people from there as well.
Okay. Sweet. Thanks.
Yeah. Are you now in Hawaii or continental US?
I'm close by, y'all. I'm in the same time zone. So I'm
Oh,
like,
you're on the east.
yeah.
Okay.
Yep.
So you're not waking up at 4 and 8 a.m.
Oh
talk.
no,
Okay.
should I have done that for some pity? No, no. I've been here actually, I think I got here last Saturday. Apparently my body can't process jet lag the same as it used to, so I'm still kind of struggling to sleep through the night.
It's only 6 hours. It's not a big deal. Okay, we'll give a few minutes. We'll start at 2:05.
Sure.
Yeah, so we'll start for those who joined. Welcome. We'll give 2 or 3 more minutes for people to join in.
Actually, I guess I can at least start sharing my screen probably.
Yeah, sure, definitely.
Let's see. Nope. Where did that go?
That looks good.
It
But
does?
it's not what it's supposed to be.
That's so bizarre. Why is this not working? No. Why is this not working?
Are you using two?
I
Do you
am.
have 2 monitors?
I do, but is there some, yeah, and I tested this out already.
So sometimes when you share, you have you click the share button, and then there are many options, many screens to choose from when you share. So you can choose the specific app that you are using for the talk, and it will go directly there.
Yeah,
That's one way to do.
let's try this again. My word. This is so weird. I've never had this happen to me. If I leave it till right now.
Of course, because It always happens when you try to do it live.
Right.
That's when things
Okay.
go wrong.
I'm gonna try to come out and come back in because
No problem. So Ashley, you can try and yeah, go ahead. I saw a white screen. Oh, now it looks good. Okay, so hello everyone. Welcome to the first TESS Science talk for the semester or the year. We are kicking things off with Ashley Chontos, and she's a grad student, although not a grad student for long now, at the Institute for Astronomy at the University of Hawaii. And she'll tell us a lot about planet and stars. And yeah, you can take it away, please.
Thank you, Avi. So you can all see I didn't realize I was just muted. So you can all see my title slide now, no problem.
Mm-hmm. Yeah.
Okay, so bizarre. Sorry for the technical difficulties. So hi everyone. As Avi just said, my name is Ashley and I am in my final year of graduate school at the Institute for Astronomy in the University of Hawaii. I work with Dan Huber on many things stars and planets, hence the very vague title. But in particular, my dissertation focuses on exploiting unique stellar populations, which we can precisely characterize in order to learn more about the stars and possible planets that orbit them. And of course, this was all only possible with the advent of space-based photometry. So the overall structure of my talk is on the left. Before I can talk about TESS, I first wanted to start with a brief summary of some things we learned from Kepler. So shown here is the population of planets prior to the Kepler space mission. The planet size is on the y-axis in Earth radii, and orbital period in days on the x-axis. This is both in log-log scale. And I've colored planet markers by their detection technique. So many of these techniques are easier for larger planets that produce larger signals. And even though we knew that, we still thought that large giant planets were fairly common. But then Kepler came along and painted an entirely different story, completely challenging everything we thought we knew about planetary science. In fact, Kepler told us that giant planet occurrence is about 1%, and that the most common planet in the galaxy is between the sizes of Earth and Neptune. Now, regardless, our very own solar system lacked analogs for both of these different planet classes, the formation and evolution mechanisms, which still remain an open question to date. Whether we have directly detected planet or an indirectly detected planet, having knowledge about the host star is important for so many reasons. Just to name a couple, well, for this group, we already know why it's important for transiting exoplanets whose sizes are measured or observed indirectly with respect to the star. For radial-velocity detected planets, the star and planet orbit about a common center of mass, and therefore this depends on both of the masses. But even for directly imaged planets, interpreting a spectrum of a planet is extremely dependent on its age. Well, fortunately, the same data that gave us a ton of planets also gave us a ton of asteroseismic detections, which currently remains the most precise and accurate way to determine fundamental stellar properties. So I figured I'd give a mini crash course into asteroseismology, what I like to call crashoseismology. I know this is a really horrible joke, but I couldn't help myself, and my name is in it, and I'll be teaching. Anyways. So I figured it would be good to start it would be good to start with the sun, the star. Figured it'd be good to start with the star we know best, the sun. So this is what an astroseismic detection of the sun looks like in brightness variations, so similar to photometry. So we have frequency in microhertz on the x-axis and power density on the y-axis. Oscillations in the sun are driven by convection. Since this is a stochastic process, you can see modes over a range of frequencies. Now I'd like to highlight a few features of the power spectrum. The first is this pattern irregular spacing. This is called the large frequency separation, or dnu. Essentially, dnu, since these are acoustic sound waves, dnu is exactly equal to the integrated sound speed profile through the star, or actually gives us the sound travel time of the star. And assuming an ideal gas law, this gives us a very precise mean stellar density. Now, if we pick a region in the power spectrum and zoom in, and just for reference, this is the characteristic frequency spacing dnu. So there's another important spacing called the small separation, and this one's particularly important because this is the one that gives us very precise ages. And finally, the shape of the envelope of oscillations is approximately Gaussian, where the peak of this envelope is the frequency corresponding to nu max, or to maximum power or nu max. And as you can see here, the sun has a nu max of about 3100 megahertz. And for those of you that aren't familiar or used to thinking in megahertz, this corresponds to a convective timescale of about 5 minutes. And it turns out that nu max scales with the surface gravity of the star, where oscillations sliding to lower frequencies would indicate a lower surface gravity, and hence immediately provides information about the evolutionary state of the star. So the two astroseismic observables, nu max and dnu, are referred to as global seismic parameters. And in fact, I thought this was a natural place to pause and mention that I have developed and released an open source package which measures those two very things. The software is called PySID, and this was initially just a translation of the well-known IDL SID pipeline, which was developed by my PhD advisor, Dan Huber, during his PhD. However, this comes with many new enhancements and improvements to the code. We tried to make it much more accessible to the broader astronomy community. It's pip installable. We have documentation there, so please go check it out. All right, so moving on to TESS. Well, luckily I'm surrounded with all the people that know everything there is to know about TESS, so I don't need to go over that. But now that we're all low-key expert astroseismologists, let's take a look at the field of astroseismology from a population standpoint to provide a little historical context before presenting an exciting TESS discovery. So shown here is the population of astroseismic detections prior to space-based missions like Kepler, Corot, and TESS. The star size is on the y-axis in solar radii, and its distance from us in parsecs on the x-axis, and then finally markers are inversely sized by their magnitude, so bigger is brighter. As expected, pre-Kepler astroseismic discoveries were limited to nearby bright stars from the ground. Ground-based astroseismology suffered from many unavoidable challenges, like aliasing from nightly gaps, duty cycles, etc. So the key takeaway here is that it was extremely difficult, and this is why there's really only 1 to 2 dozen confirmed detections from the ground. But then again, Kepler to save the day, which revolutionized the field by adding thousands of detections, thousands of oscillations and stars. However, as one can see in the figure, many points that were added, but they were quite small. And it's true that most Kepler targets are distant and faint, and therefore we only have limited constraints from other independent classification methods. But as the TESS mission continues, we expect that it will naturally fill in the middle region in this figure, bridging the gap between the closest, brightest ground-based detections with the faint, distant Kepler detections. And hopefully a lot of these purple ones will become orange. So now I'd like to draw your attention to the roughly solar-like region, which I've just added arbitrary lines as a visual guide. So you can see that even with the thousands of detections that we have, detecting oscillations in true solar-like stars is actually quite difficult. Well, spoiler alert, it's not too difficult for TESS, which was able to detect oscillations in this late G7 dwarf, which was a really important discovery for the mission, and I'll discuss why in just a few minutes. So Alpha Mensae is now the closest solar analog for which we have a detection from an astroseismic detection and characterization from space, but also it's the coolest star from the nominal mission for which we were able to do astroseismology, literally the coolest. So this was particularly exciting, but one of the main reasons this was possible is because the Mensae constellation is near TESS's southern continuous viewing zone, of which I'm showing the year-long light curve here for. By the way, for reference, Alpha Men is a naked-eye star and it has a visual magnitude of about 5. So if we take the Fourier transform to compute a power spectrum, this is what we'd be looking at. So on the left is in log-log scale and on the right is in linear scale. So we modeled the correlated red noise structure so we could subtract that from the stellar contribution from the power spectrum. And actually that's what I'm showing on right. On the right is the background corrected power spectrum. So we use the shaded region that I've shown on the right to compute an autocorrelation, and that's shown in the inset. So basically, given the region of oscillations, we can very precisely, or we can basically estimate what the expected spacing would be fairly well. And I'm showing that by the blue dashed lines, and then I have some fractional harmonics shown by the red dashed lines. So therefore, if we see strong peaks at these expected spacings, then we can quantitatively confirm the oscillations. And as I mentioned before, frequency scales with the log g of a star. And as we just saw, the sun has a nu max of about 3100. So specifically for this star, a higher nu max immediately implied a later type star than the sun. And this was actually consistent with the G7 classification from an earlier paper. So now perhaps the more exciting part of the discovery was that there was a known bound mid to late M dwarf companion. And this was first discovered by Eggenberger et al. In 2007, or at least that's where their initial classification was. So fortunately for us, the M dwarf companion was also resolved in Gaia DR2, which we could now combine with the astroseismic analysis, in particular the age, to precisely characterize the M dwarf, which is typically otherwise very difficult to do. So M dwarfs are notorious for their slow evolution in fields like gyrochronology, which produce rotation-based ages, are really promising for aging later type stars, but often lack calibrators in this regime. In fact, what we ended up doing was using a very precise population of M dwarfs from a paper by Andrew Mann in 2015, and combined it with Gaia information to derive empirical relations for M dwarfs using the Gaia magnitude and metallicity. So this is actually fairly new work and not yet available, as the original paper was submitted prior to the availability of EDR3. But to circle this back around to exoplanets, there was a recent review by, well, I guess not recent much anymore, but by Belikov in 2015 showing essentially the past, present, and future potentials for direct imaging missions. And if I had to put this on a timeline instead, it would look something like this, where we're right about here. So in the upper right-hand corner of the figure, the current population of directly imaged planets, which are young self-luminous giant planets, because that's about all we can do at the moment. We're essentially entering the ground-based ELT regime that are capable of imaging potentially habitable planets around the nearest M dwarfs. But for future space-based imaging missions like LUVOIR and HABEX, we think we'll finally be sensitive to imaging true Earth analogs orbiting solar-like stars. And out of curiosity, I wanted to see if Alpha Men was on this plot. And sure enough, here it is. So with the astroseismic age and characterization, Alpha Men should be one of the prime targets for the next generation of space-based imagers. So no planets there yet, but possibly. And before I move on to the second half of my talk, I wanted to show some newer unpublished results. So going back to the power spectrum that was used in this paper and that I just showed, this time I've added the original power spectrum in gray. So now had we not used smoothing filters, the oscillations might not have been detected, since they are clearly consistent with the noise properties. That being said, we were still able to produce an age to a fractional uncertainty of about 20%. And this was cautiously and conservatively selecting the oscillation modes that we used for modeling. In fact, I think we used peak bagging results from 4 different methods and rejected any modes that were not unambiguously determined by all 4 methods. Okay, but now we have the 20-second data, and my curiosity got the best of me, and even though my advisor told me not to, I decided to check. And this is what the fast cadence light curve looks over the same baseline using the 20-second data. It's just spectacular. So yeah, TESS fast cadence data looks very promising for bright K-dwarf asteroseismology. And so before I move on to the second part of my talk, I just wanted to pause. I'm not sure if this is like more informal, people can interrupt and ask questions, but I just wanted to see if anybody has any questions before I move on.
Hi, Ashley. This is Sarah. I have 2 questions.
Sure.
First of all, pi, I always forget what it's called. Pi men A, I think. Pi men A.
Pi men. Are you talking about, oh, this is alpha men, actually.
Oh, alpha men. That's what I meant. I get it confused with the so-called Chelsea planet. So what's the rotation rate of that star?
Great question. We don't know.
Oh, we don't know, but I thought you could get that from, oh, because you don't see rotational splitting. Okay. My second question was, I've forgotten, I read the paper, but for the 22nd paper, what are like, let's say the top 3 reasons why the 22nd data is so much better? I think one has to do with cosmic rays, but.
Yeah, I think, so Dan has spent a lot of time thinking about this. I think there are probably people in the audience here that could say more about the cosmic ray rejection, but from the observational asteroseismology perspective, the fast cadence data, well, one, there's this attenuation of the signal due to time averaging. So for TESS short cadence data, the Nyquist frequencies was 4,200 megahertz, and for alpha men, which is it's somewhat close to that, the attenuation factor is already 40%. So we're only seeing about half of the signal. Whereas for 22nd data, the Nyquist frequency is like way up in the tens and thousands. So you can see that the actual amplitude of the signal is much better.
Okay, thank you.
Yeah.
Yeah, Sarah, I don't think it has as much to do with the cosmic ray rejection as what Ashley was saying. There are effects from this is a 5th magnitude object.
Yeah, I don't care about cosmic rays. I just couldn't remember, so I was just throwing something out there. Just was trying to get a handle on the top factors. Thank you.
Yeah. So that's a bit of a red herring. So okay, thanks.
All right. Awesome. So, as I mentioned earlier, ground-based follow-up for Kepler targets was extremely challenging, but fortunately, TESS is finding transiting planets right in our solar backyard. This means that TESS planets are much more amenable to RV follow-up, thus making it easier to precisely determine the properties of these systems. So, the TESS-Keck Survey, or TKS for short, plans to do just that. And TKS is a very large collaboration amongst partner Keck institutions, which was awarded several nights over multiple semesters. In fact, if you'd like to learn more about TKS, including the science goals and how we converged on a final target sample, I submitted a paper a few months back that discusses this all in great detail in case you missed it. And the paper is actually meant to be the first in a series of ensemble analyses from TKS. But to briefly summarize the main TKS science goals, there are 4. The first is focused on the bulk compositions of small planets. Again, this is further exploring the super-Earth and sub-Neptune classes I mentioned earlier, measuring the precise masses, densities, compositions, and orbital properties for these systems to understand how they form and evolve. The second is more from a dynamical perspective. So this is including anything and everything from eccentricities, obliquities, multiplicities, including how they tie into different observed populations. The third science case is identifying prime atmospheric targets for JWST. So this requires precise mass measurements to both differentiate between degenerate models of interior compositions, but also to break the degeneracy between surface gravity and the atmospheric mean molecular weight when interpreting their transmission spectra. And of course, last but not least, focusing on planets orbiting more evolved stars, or TKS evolved. And then also we have a couple technical outcomes, which here just means that these are also catalogs and studies that will naturally fall out of the survey, but we're not necessarily requiring any additional telescope resources. So this includes the homogeneous characterization of TKS stars, as well as looking into the overall, the activity characteristics of these stars. So in the paper, we provide our full sample. And this is one of the figures in the paper, and this is showing the full TKS sample broken down by those 4 main science themes, including, and this also shows which targets will be used to address which science cases. So the top 2 panels are the stellar parameters. The left is in HR diagram, and on the right is in mass metallicity space. And then the bottom two panels are the TKS planets. The left is showing the planet size versus orbital period in days, and on the right is an incident flux space, still with the planet size on the y-axis. So here concentric rings represent targets that were selected by multiple science cases. So it's worth noting that we implemented a unique hands-off target selection algorithm that encouraged this target sharing. The overlap, which is even more clear in this Venn diagram, demonstrating the proof of concept. So the code and everything I used to construct this target sample is publicly available. The link which is in the paper in case you are interested. Now to throw up some current numbers for TKS, if we go back to the paper, TKS initially proposed for 103 planets and 86 systems. Actually, which in hindsight is a bit misleading, since 25 of these targets are in our distant giants case, and therefore we won't expect to get precise masses for that. So it's actually 78 planets that we intend to get better than 5 sigma masses for. Now for confirmation or greater than 3 sigma masses of the planets, we're about 2/3 of the way there. And actually 10 of the 25 distant giants programs have significant trends, so even that program is showing some promising results. For publications, TKS is leading 13 publications characterizing 24 planets and 16 systems, where students are leading a majority of these, by the way, with 8 papers. Additionally, TKS has contributed RVs to 7 other non-TKS led papers, and also we just have a bunch of other stuff in the pipeline, so stay tuned. And now going back to this figure, the rest of my talk will be discussing the obvious outlier in all of these parameter spaces, which is TKS evolved, and is a large part of my dissertation work. And in particular, this is focusing on exoplanets orbiting TESS subgiants. Okay, so why subgiants? To motivate this, I want to just show this great figure from a 2018 review by Rebecca Dawson and John Johnson discussing the origin of hot Jupiters, one of the first ever planet types to be discovered, and it still stumps us to this day. Where did they come from? How did they get there? And in particular, I really like this table because it synthesized all of the information, literally decades worth of work, into a single table. The table contains the 3 main popular hypotheses for hot Jupiter formation, which is in situ formation, forming beyond the ice line, the snow line, and then migrating in, and then high eccentricity or tidal migration. Basically, each have their checks, which are good, some X's for inconsistencies, but as you can see, each has its own strengths and weaknesses, and there's no single great answer for any of these processes for the observed population of hot Jupiters. So one of the main takeaways that I at least got from this table is that stellar ages might help here. And this is where my program comes in. So stars spend considerably less time on the subgiant branch with respect to the main sequence, that even a basic location on an HR diagram gives us not only a very precise mass, but also a precise age. And this is particularly true now that we have Gaia. So at least on a relative scale, we should know these ages fairly well. Moreover, our sample will be naturally biased towards larger planets, so this might help inform some of these theories. Okay, so what does the sample look like? The survey started in semester 2020A, I believe, so I think a lot of the targets are reaching or approaching to your baselines. So this is the down-selected sample of TESS planets orbiting subgiant stars in an HR diagram and in planet size incident flux space. The program targets were selected based on detailed vetting reports and what I felt were the most promising targets, but they also nicely and conveniently span a nice range in both stellar and planet properties. The colors in the plots represent the mass significance we have for the planet, so the darker is a more precise mass. For numbers of the total, I think there's 24, we already have confirmed planet masses or greater than 3 sigma masses in 13 of these systems, and about half of these have better than 10 sigma masses. Plus, you might notice some orange ones, which are non-transiting planet detections detected in radial-velocity space. So we're doing quite well. Now, I'm going to highlight some new TOI planets that I think are new anyways. And because I haven't really had a chance to talk about this publicly, about any of these awesome planets, and this seemed like a very appropriate audience too, I've included an ambitious 10 plus planets, so I'm just gonna like zoom through them, but by all means feel free to stop me if I'm going too fast. So we're gonna start big, actually massive. So this is TOI 2145. Initially this system wasn't totally very interesting to me until I started diving into the literature. The host star is quite massive at 1.7 solar masses. This is just assuming solar metallicity grid, so it's actually metal rich and therefore more massive. As you can see, the planet is a fairly close in Jovius-sized planet, which is actually right on the warm to hot Jupiter regime, I think. Yeah, so it has an orbital period of 10.2 days. So we started collecting RVs for this system, and you can see in the lower panel, C, in the bottom right, it's quite massive itself. So these planet types, dubbed super Jupiters, are fairly uncommon, especially closer into the host star like this. And I think the number of super Jupiters for which we have both a measured mass and radius is like 6. Anyway, so it's hypothesized that for more massive stars, which have more massive disks, that the disks dissipate more quickly, which halts inward migration, leaving planets stranded at several AU. Additionally, so in addition to this planet, if you look at the residuals in the lower left-hand panel and panel B, you can kind of see some I don't think you can see my mouse, probably can't see my mouse, but there's kind of some like up and down behavior, some correlated structure in the residuals. And it turns out that a single planet model wasn't doing a great job fitting the data. And then we introduced a second planet, and it seems to prefer the 2-planet model with an additional less massive planet exterior to the super Jupiter near a 2-to-1 resonance. So that's interesting. Of course, we need more RVs for this system, but let's see. Next system is TOI 1439, which is a more solar type star in terms of its age and effective temperature. The planet is Neptune size, and at least for TESS standards is on a longer orbit, which is essentially the same length as a TESS observing sector. When we initially started following this TOI up, the mass was coming in, I think, at about 40 Earth masses, which for a 4 Earth radius planet seemed to be on the more massive side, so we thought it might have been the stripped core of a large planet. But however, there's also still a fair bit of scatter, and this is actually not what we expect because it should be a fairly quiet star. So again, we carry on, collecting more RVs for this system. The next system, there's actually a funny anecdote I'd like to share. By the way, this is for TOI 1736. TOI 1736 has a small transiting planet, the size which differs between pipelines, and admittedly I haven't fully modeled it yet, but still sub-Neptune sized. The system is a bit older, as you can see, almost double the age of the solar system. Now, what first stumped me about this system was interpreting the DV reports, and there were several, and I've looked at many DV reports. So essentially, there were several TCE reports generated for the same planet, because I checked, but they each had slightly different periods. Now, I hadn't seen this before, but my most obvious thought was, is this TTVs? Can we do, like, is this a thing? So I showed it to the rest of the TKS group. They also agreed they hadn't seen it before, but thought it was interesting enough to follow up. And turns out that that's probably what it was, since there's a massive outer companion for which we're still trying to lock down the properties for, as you can see in the lower right. So actually the outer companion isn't even included in the population plot on the top, because I think it would technically be off to the right of the second plot there. Yeah. So TOI 2019 is interestingly sized. It's a bit larger than our typical Neptune-sized planet, but it's also a bit smaller than our usual sub-Saturn candidates. Therefore, I'm really interested in getting a precise mass and density for this one. Turns out it hasn't been very easy so far. I think we've gotten more than 45 RVs currently, and it just set. So we're going to have to wait before we can learn more about this one. It is suggesting that there's another planet. I didn't include it on the population plot, so I'm not quite convinced myself yet. Yeah, I think that's all I wanted to say about that one. So this is another one of my personal favorites, TUI-1605. So there are many theories that suggest hot Jupiter engulfment happens quite early on. The circularization, which is supposed to happen faster than inward migration. However, this system tells a different tale. So we are in the hot Jupiter regime at a period of 8.7 days. We also have a significantly non-zero eccentricity. And given the age, we wouldn't expect either of these things at an age of 8 gigayears. However, we also do have a significant trend suggesting an outer companion that could have dynamically interacted and scattered this planet, or potentially excited the eccentricity, or both, or something. So what's the next one? Oh yeah, okay, TUI-480. Yeah, this is another great one. Sorry, I'm probably going to say that about all of the planets because I'm absolutely biased, but the star is younger and the planet sits just outside the sub-Neptune desert. Now, the expected Doppler amplitude of the planet is 3 meters per second, and the V sin I is a whopping is 9 kilometers per second. So we're trying to get this weeny amplitude from that signal. So yeah, we knew what we were getting ourselves into. I think nobody else is following this up, or at least last I checked, it's probably because of that. But because it was bright, we figured we'd give it a go and make it a nice borderline case. Remarkably, we are getting a better than 3 sigma mass using the TESS period and ephemeris. Also, we have been doing triples, so anytime we observe this, we're getting triple shots to try to get around the scatter. So the RV time series I'm showing in the, in the panel A is binned nightly, but if we look at all of the RVs, you can see that there's kind of this periodic nature on the order of hundreds of days. And this is also lining up with a peak we see in the RV, the periodogram of the RV residuals near 113 days. I think we also have a tentative astroseismic detection in this system as well. So, all right, TUI-1181 appeared to be a superinflated, very hot Jupiter residing on a period of only 2 days from its host star. It is also on the younger side, consistent with the hot Jupiter story. However, the mass seems about right for its size, and it is on a circular orbit. This one has a large V sin I and also a large RP over R star, so we decided to measure the RM effect. And isn't that just the most beautiful aligned RM curve I've ever seen? Clearly an aligned circular hot Jupiter. So this one seems to be behaving as we'd expect. I'm going to skip this one. Okay, so TUI-1898 is actually a funny story as well. You can see that early on in the RV time series, in the panel A there, you'll see the green. It was actually being observed with the Automated Planet Finder, or the APF. This was courtesy of Paul Dalba, who's a TKS postdoc, and has been working a lot with the single transiting planet candidates. At the time, I didn't know this, and also started following it up with HiRES, the two which kind of together saved the day and rescued the period for the single transiting planet candidate. I've highlighted a few points in the fit where something just didn't really seem to add up. Can't really see it in that third one, but in the middle one you can see it quite clearly. Initially, I thought we were getting the period wrong since we do only have one transit. However, when we injected another planet, it seemed to do a pretty good job describing the system. And because of the extended baseline and additional phase coverage from the APF that the APF gave us, we were able to get a 3 sigma mass that was constrained on a planet at roughly 2 times the period of the inner. So this one was interesting to me because eccentric warm Jupiter seemed good for high eccentricity migration theories, but the somewhat close companion is not. The 2-to-1 resonance, which would be more consistent with the migration story. So anyway, yep, another one we need more observations for. I think this is my last one. So some of you might recognize the TOI number, TOI-197. For those that do not, this was TESS's first astroseismic host, written up in a paper by Dan Huber, Bill Chaplin, myself, and much of the TESS community. And this was essentially our first light paper for solar-like oscillations working group. What's really interesting about this system to me is that we used 5 different telescopes / instruments over, I think, roughly 4 to 5 periods of the planet. So collective baseline about 50 to 60 days. Actually, I did the joint modeling myself, which is shown in the lower left-hand plot. So that's taken directly from the paper. So I fit the transits, RVs, and astroseismology all together. This came up with a planet mass of 63.4 plus minus 5.7 Earth masses, so better than 10%. Weirdly enough, with more high-res RV points, I became less convinced of this. So I continued to follow it up, actually still continue to follow it up. And I'm glad that I did, because there's very compelling evidence for an inner non-transiting planet at a 2-to-1 resonance. But also, if you take a look at panel C, you'll see that the planet mass is nearly 2/3 lower than what we originally published. And if real, the smaller planet sits on the upper edge of the sub-Neptune desert. So eventually, when I'm done with the postdoc job application struggle, I will get back to this lovely sample and properly model all of the properties of these systems. They come in all different shapes and sizes. We have stellar ages. We have a wide range of stellar masses. And the idea is that we want to compare population level properties to their main sequence and red giant planet population counterparts. But also because we have such a nice diversity of large planets, we can revisit things like what I had discussed earlier about hot Jupiter formation and migration, and maybe even tie in some of the ages that we have to better constrain some dynamical timescales over which some of these processes occur. I'd like to just say that the unique thing about our program is that we aren't just following these up for confirmation, we are continuing to follow these up today. So we're probing long-term characteristics in the systems, therefore sensitive to the eccentricities in these systems, the multiplicity of these systems. So stay tuned. I'm currently working on the catalog page. Actually, that's a bold-faced lie. I'm currently working on applications, but eventually I will get back to this. But speaking of job applications, I've been future tripping a little, so I just figured I'd close the talk out with some future prospects, which brings me back to an earlier point I made about the TESS 20-second data. And in case you already forgot how amazing it was, let me remind you. So with the new 20-second data, we'll be able to get great ages and possibly even some inclinations for solar analogues. And I brought it back to Alpha Men because Alpha Men is a solar analog, and therefore a perfect example. And the application and utility of asteroseismology within the exoplanet community is twofold. And so this is going back to another plot I showed earlier, except this time I'm also highlighting seismic stars with known planets. So for astroseismic hosts, the application is more direct since planets orbiting astroseismic stars already account for some of the most precise and accurate planet properties that we know about. But even for stars that do not host any known planets, we all know this could change, in particular for future imaging missions from space hoping to image these true Earth analogs around true sun-like stars. Age is a very important factor. So the unique age and inclination constraints from astroseismology remains unmatched and could be quite helpful for informing future imaging surveys. So this is what I would hope to do if I get a postdoc this round. So I figured I'd leave this figure up and take any questions.
Actually, I've got a question. Looking at this last graph, of course, Tau Ceti has a lot of references in science fiction and such. My question really is, has TESS been able to add very much to what was known from prior observations to that? And if so, which areas have the TESS observations? I mean, it's quite a bright object, of course, so it must be somewhat challenging to do the analysis for it.
Yeah, well, I hate to disappoint, but I haven't taken a look at this particular star yet. It is funny you mention it, though, because Dan was actually just commenting on general population level characteristics, and that he thinks that TESS will be able to do all of the purple except for Alpha Cen B and Tau Ceti, and I forget what his reason was for Tau Ceti, and sorry, my cat wants to be a part of the Q&A here, but I would have to get back to you on that. Yeah.
Okay, thank you.
Yep. Sure.
Any other question? You can just unmute yourself or raise your hand, virtual hand. Prajwal, please go ahead.
Hi, Ashley. Great talk. I was wondering about, you mentioned the library SYDS, right? I was wondering, how is the algorithm different from Lomskargol? And I was also wondering, in terms of the algorithm, how do you handle transits and stellar rotation?
You're saying for PySid?
Yeah, PySid, yeah.
Great question. So PySid is currently designed to only do frequency domain stuff. I've been trying to implement time domain tools, but I haven't convinced my advisor that this is worthwhile. So typically from my end, when I do processing of light curves for astroseismology, I definitely get rid of the pesky transits, because we don't care about the planets, right? We care about the stars. Don't tell anyone else I said that. And I'm sorry, I think you asked something about the Lomskargol periodogram.
Yeah, how is it different, the algorithm you use in there? Is it?
It's, well, again, we're actually not computing the power spectrum. We're assuming that the user provides an input time series and power spectrum, but we are actually just using the basic, or at least I use the basic Lomskargol periodogram from SciPy or AstroPy. I can't remember which one it is off the top of my head.
Thank you.
Yep, you're welcome.
Any other questions?
Just leave those there for you.
Okay, one quick question I had is, you mentioned a smoothing filter. Could you say a little bit more? What does that include?
Sure. Let me just pull up that. Actually, we'll go to this one. Yeah. So smoothing filter is essentially just you can think of it as just binning the power spectrum. So it's not doing anything to it's not manipulating the power spectrum at all. It's literally just used as a visual aid. And because I was used to, and my first year project, or my first grad project was looking through reprocessed Kepler short cadence data. So I was going back through to try to find really low SNR detections. So these are the kinds of things that you use in those types of cases. And you can actually, you can see that, like with the gray on the left, you might not look twice at it, but when you apply the smoothing filter, it kind of just pops out, just a way to average over the noise, in a way.
So it is smoothing that done in frequency space?
Yes.
And nothing is really done in time domain?
No.
It's only like get the periodogram, go to frequency space, and then start the
That's
cosmetics.
not always true. We can apply high pass filters, which will just remove a bunch of the excess power at lower frequencies.
Right.
But that was not the case here. I don't know if that just confused you more, but there are things in the time domain that we can smooth out to get rid of, like I said, high power and power leakage into higher frequencies.
Yeah. Prajwal, you had another question?
Yeah, I had another question. I was wondering, so I think in your plot for the size of the planets, you had some of the planets that were like twice the Jupiter radius, right? Were these all highly irradiated planets?
I'm trying to. I'm thinking TOI 1601, 1294. I'm pretty sure that a bunch, all of the, at least the 4 that have 10 sigma masses,
yeah,
are actually all greater than 1 Jupiter mass. So it would seem actually not consistent with that. Although, like I said, I haven't done any of the detailed modeling, so I can't say for sure. But I know that they're not like your typical 0.5 Jupiter mass planet.
I was more interested
too.
Sorry. Yeah, I was more interested in the radius. So you have like some of these inflated planets, right, that has radius greater than 1 Jupiter radii. Are these all highly irradiated planets? Like, is the temperature really high or above 100,000 Kelvin? Or sorry, 1,000 Kelvin?
Yeah. Well, so the one that's in the uppermost, the upper leftmost corner, that's TOI 1181. That is on an orbital period of 2 days, so you can see it receives like a whopping several thousand the Earth fluxes. So I don't know what the equilibrium temperature is off the top of my head. I know it's scorching. So I'd imagine there's probably some interesting physics like that going on, but I haven't explored that yet.
Thank you.
Sure.
Any other questions? Comments, thoughts, feedback?
Feel free to contact me offline too. Happy to chat.
Yeah, so I CC'd Ashley on the announcement of this talk, so you all have her email in that message, so you can contact her directly. And Ashley, you mentioned you're on the East Coast now?
I am 45 minutes outside of Boston, so you also might just see me wandering halls.
Right, so we might want to arrange like having you come visit MKI. Things are now, I think, starting to settle down into some kind of routine at MIT with the testing, and so far the positivity rate is very small. So we should definitely keep that in mind in the next few weeks.
Sure, I would totally be down for that. Actually, that's why I'm here. So yeah.
Okay, last chance for any questions. Okay, if not, thank you, Ashley. That was very interesting to see, at least for me, I hope for everyone else, to see that asteroseismology side by side with detection of planets. And personally, I like this detection of planets around evolved stars. I think it's very interesting for many, many reasons. I did learn a few things on top of seeing exciting discoveries from TKS, which is probably just the beginning. So that is actually makes me a bit envious, but okay. So thank you again. So for everyone, next week we have Daniel, who is a new or relatively new postdoc, TESS postdoc, who is now on campus. So he will give the TESS science talk next week. I'll send a separate announcement. So I'll see you all next week, and have a great rest of your day.
Thanks everyone for coming.
Thank you. Thank you for a wonderful talk, Ashley.
Thanks
Yep,
for
great talk.
See you.
Bye.
Bye.